to start talking about mass spectrometry, and today we're going to talk a little bit about how the technique works. On our next lecture on Monday, we're going to talk about concepts, and then on Wednesday, we'll spend one lecture on EI fragmentation, which is kind of special topics. It used to be really, really central to mass spectrometry. It's sort of part of pedagogy that's carried on, but EI mass spec is the historical first in mass spectrometry, but is a lot less important these days. Mass spec is a super important technique. Molecular weight and molecular formula are some of the most fundamental things that you can get, and mass spec is easily a technique to give you molecular weight. We'll talk about high-res mass spectrometry. From that, you can get molecular formula. We'll talk about that next time and the concepts that are associated with that. One thing that mass spec can easily talk to you about is elements present. And this is really important because you can easily see bromine and chlorine. You can see sulfur and silicon if you know what you're looking for. And what's valuable about that is NMR is not going to be a technique that talks to you about elements like that. IR is not going to be a technique that talks to you. So this is why you should be reading these spectrometric techniques. And these days, mass spec can also be incredibly valuable in getting structure. It's in fact become central to biomolecular mass spectrometry, to sequencing peptides and proteins, but also for more traditional organic structures and natural products. You can get structure through fragmentation patterns, which, as I said, we'll be talking about a little bit on our third lecture. And as I said, in biomolecular cases, through slash techniques, through techniques like MSMS, where you're actually taking ions and deliberately bashing into them and smashing them and see how they break up. All right. The basic principle of mass spectrometry is super simple, like beginning physics. The basic principle and I love making these very simple-minded drawings of scientific instruments because it's a good way to get into our heads how the basic technique works. So if you want to think about the basic technique, you can think of an ionized molecule. And that ionized molecule is moving along until you come to some sort of magnetic field. In the simplest and historical realm, it is literally an electromagnet. And as the particle moves into the magnetic field, its path gets bent. You have a force on it, right? It's all that right-hand rule stuff from physics. The degree of deflection depends on the mass to charge ratio. In other words, any given particle, whether it has 20 AMU and one charge or 40 AMU and two charges, is going to get deflected the same amount. So it's the mass to charge ratio that you're seeing on the x-axis not M to Z, not mass. This becomes particularly important when you're doing EI mass spec, which we do a lot of here in the facility. ESI, electrospray ionization mass spec, and you do it on reasonably big molecules where many times you get more than one charge on a molecule. The degree of deflection depends on the mass to charge ratio. Not surprisingly, a heavier H-E-V-I-E-R, I can't spell today, is deflected less. A heavier particle is more massive, so it's going to get bent less. More charged is going to be deflected more. And it's amazing how easy it is for people to lose sight of these principles, particularly when you're starting to talk about fragmentation, in that everything you see in the mass spectrum is going to be charged. In other words, a free radical, R dot, that has no charge on it is invisible. Something has to have a charge. Most of the mass spectrometry you're going to do will be in the positive ion mode. In fact, that's all we're going to talk about today. But one can also do it in the negative ion mode, where you're looking for negative ions. Most of the molecules that one works with don't have a charge on them. So the first question is, how do you get a charge on the molecule? Historically, the first technique developed is called electron ionization. You'll see that written as EI, or you'll see the whole technique written as EI mass spec. And the basic idea is a little counterintuitive. You're going to use an electron to ionize the molecule. So far, so good. You have a molecule. You fire an electron at it. You accelerate electrons and give it a good hard whack. What's counterintuitive, when you give a molecule a good hard whack with an electron, you knock an electron out of it. So you get a cation. Electrons weigh virtually nothing compared to molecules, so for all intents and purposes, the mass is the mass of the molecule. So for example, if you take methane, CH4, and you hit it with an electron, you get CH4 plus. You've taken an electron out of it, so you're getting a radical cation, what mass spectrometrists call a molecular ion, and your two electrons. As organic chemists, we have trouble thinking about odd electron species. Most of the species we deal with have even numbers of electrons. In fact, I think by the time a student has taken sophomore organic chemistry, it gets more perturbing to see a structure like this than when they're a freshman. Because as a freshman, you just learn, okay, you count up the number of valence electrons from carbon, you count up a number of valence electrons from hydrogen, you take away electrons. And so a freshman confronted with the problem of writing a series of Lewis structures and resonance structures for a molecule like this, we'll dutifully go ahead and say, well, okay, we've only got 7 electrons, so I guess we've got to make do with our 7 valence electrons, and I can write a resonance structure like this, and I can write a resonance structure like this, and I can write 2 more, I'll just write etc. And we have a net positive charge. But by the time we get to organic chemistry, it gets perturbing to think about this. If you like to think in orbitals, you can think, okay, we're just knocking an electron out of the highest occupied molecular orbital. And you can just think of this species and say, okay, instead of having a filled highest occupied molecular orbital, we have a half-filled highest occupied molecular orbital. Conceptually, it gets easier when you have obvious orbitals, when you have things that you can see rather than molecular orbitals. So in the case, for example, of anything with a lone pair, such as an ether, if you go ahead and you take away an electron, whoops, that's minus E minus. If you take away an electron from this, you can say, okay, it doesn't look very good, but there's my molecular ion. There's my radical cation. If you have an alkene, you can say, well, the pi orbital is the highest occupied molecular orbital, so we're going to take an electron away from it. I can write a resonance structure like so. And a second resonance structure may be perhaps a more minor contributor, where I just swap the charge and the odd electron. Thoughts or questions?
About not being able to see a radical on...
Exactly. So later on when we start to, so the question was about not being able to see a radical. So when we start to talk about fragmentation, you'll see a little bit of this because at the end of today's class, I'll even show you an ESI mass spectrum where a molecule does break apart. When one of these radical cations breaks apart into 2 halves, one half will end up with an even number of electrons and a positive charge. The other half will end up with an odd number of electrons and no charge. And the radical, because it doesn't have a mass, it doesn't have any charge, won't be deflected and won't show up and won't be detected because the detection depends upon detecting an electrical current. So for example, later on we're going to see that if you have an ether like, I'll make it simple, like diethyl ether, and this molecule breaks apart, because when you give it a whack with an electron, you put a lot of vibrational energy. So you've done double damage to the molecule. You've decreased the number of bonding electrons, so you've weakened the bonds in the molecule. And you've put a lot of kinetic energy into the molecule in the form of the impact from the electron. So the molecule now is vibrating, it is hot, and it has a tendency to fragment. And so, for example, if diethyl ether fragments, and I can write a curved arrow mechanism for the fragmentation, we'll talk more about it later, you get CH3+, and you get this charged species, and you will observe this species, but you will not observe the radical. Does that make sense?
I'll ask you a question after.
All right, let me give a little more detail on the instrumentation of an actual EI mass spectrometer. So what I showed you before was sort of a simplified diagram. And I'll still give you a simplified diagram. Now, the first thing that you need to think about is all this chemistry, and this is true for all of mass spectrometry, occurs in the gas phase. In fact, for common techniques that an organic chemist would use, it's the only experiment where you're doing it in the gas phase. IR, you could do gas phase IR, but most of the molecules organic chemists work with are going to be in the liquid phase or the solid phase or the solution phase. So the first problem is, how do you get the molecule into the gas phase? So typically what you do is you have a heater, a coil of wire like a filament, and you put your sample on the filament, and you have this in a vacuum. And it's going to need to be a pretty good vacuum, at least by the time the molecule's flying along. The ionization part can have some pressure to it, but by the time the molecule is actually moving, you've got to have movement in the vacuum without it colliding into other molecules. In fact, one of the experiments that people sometimes do are collisional experiments where you're deliberately trying to stop the motion of the molecule, but short of those experiments, you need the molecule in a vacuum. You then have to, so you have to get it into the gas phase. Already this means that EI mass spec is going to be limited to molecules that can be evaporated. That means that by the time you get to very big molecules like strychnine, which are going to have very, very low vapor pressures, even at high temperatures, you're fighting getting it into the gas phase, because if you heat it a lot to get it into the gas phase, you're going to basically cook and decompose the molecule. Once you get the molecule into the gas phase, you hit it with an electron beam. That electron beam typically ends up being at 70 electron volts. The molecule now in the gas phase is ionized, but it's not moving at any particular rate. So then what you do is you have a pair of accelerating plates. Those impart velocity to the molecule. And then, as I said, we will, in what's called a magnetic sector instrument, the oldest sort of instrument, have a magnet, an electromagnet. The molecules will move in, and depended on their mass to charge ratio, will go to a detector. And the detector basically measures electrical signal. The molecules are charged, and so you get a current, and you can amplify that current and therefore send that current on to a recording device or a computer. So this is called a magnetic sector instrument, and what you typically do will be vary the magnetic field. And in doing so, as you increase the magnetic field, those molecules that are deflected less will then get deflected more. And if you plot versus magnetic field the current, then you basically get a graph, and that graph translates to mass to charge ratio as a versus intensity. So on the x-axis, you will see m to z. And on the y-axis, you'll see intensity of the current. And of course, you'll see some patterns associated with the molecule and with fragments and with isotopes that we'll talk more about in a moment. And this will be called a mass spectrum. And in a way, the technique is a misnomer because, of course, a mass spectrum is not a spectrum. From the earliest points you're learning science in school, you learn that spectrum is electromagnetic frequency, And here, of course, this only looks like a spectrum. It looks like an NMR spectrum where you have frequency on the x-axis in hertz, which translates to parts per million, or an IR spectrum where you have frequency in wave numbers, which is just a frequency unit, or a UV spectrum where you have frequency or wavelength. James?
So the detector produces a current. How does it produce the current?
Well, very simple. If you have M plus, a charge, going to a detector, that means you've got electricity going in. And so you send that to an amplifier, just like a microphone in your cell phone generates a minuscule current, and then it goes to an amplifier and then gets broadcast, actually gets digitized in that case, and gets broadcast, goes to amplifier to a computer. Actually, in a modern system, it would go to an analog to digital converter, and then it goes to basically a printer. But in the oldest systems, of course, it would go to an amplifier and then a strip chart recorder, because you could literally just go ahead and have a needle go or another electrical signal to write on a piece of paper. Good question. Other questions? There are lots of variations, and if you talk to John Greaves, he will wax. John Greaves runs the mass spec facility. We have one of the premier mass spectrometry facilities in the country. It's probably the best on the West Coast here because of John's innovation in putting together a really great facility with a whole bunch of instruments and great support and open access, and you can go there 24/7. If you talk to him, he will wax poetic about different sorts of detectors and so forth. So for example, another detector that's used is called a quadrupole detector. And the idea on the quadrupole detector is you have 4 electrical rods, 4 metal rods. The ions come into the rods, the detectors at the end. You have alternating current of varying frequency on the rods, and ions of different mass charge to charge ratios get through at different times as you vary the frequency. And so a quadrupole detector is another way rather than a magnet. Another way that you'll see is called time of flight, or TOF. And the basic principle here is that when you accelerate particles across a certain voltage, if they're heavier, they're going to be moving more slowly, and so they'll take longer to fly. And that's used in particular with various laser techniques like matrix-assisted laser desorption. So one of the problems with EI mass spec is that you put a lot of energy into the molecules. Often they fragment, so often you're not seeing the molecular ion. You're not directly getting the molecular weight, but you're inferring it from the fragments that are developed. There are a whole bunch of other ionization techniques, and these are important because often you get less fragmentation. So in addition to EI mass spec, electrical ionization, there are a bunch of techniques that are called soft ionization techniques. That are less prone to fragmentation. The first developed is CI, or chemical ionization. And the big difference between chemical ionization and electrical ionization. And the big difference between all of the soft techniques and electrical ionization is instead of knocking an electron out of the molecule, you're putting something charged onto the molecule. Often what you're doing is adding a proton to the molecule, which in a way is much more intuitive to an organic chemist because you're basically using a strong acid or using an acid of various forms to protonate the molecule. One of the problems of chemical ionization and one of the problems of electrical ionization is over here, getting the molecule into the gas phase. As organic chemists and biomolecular chemists have become interested in bigger and bigger molecules, the targets of organic synthesis have gotten bigger. People are interested in proteins and nucleic acids and oligosaccharides. As all of the molecules have gotten bigger, the issue of ionization has become more important. Another technique that's been developed is called fast atom bombardment. And I'll show you more about these in just a second. There's a variant of this technique referred to as LSI. In one case, you're doing the business that I'll show you with an atom. In the other case, with an ion. And MALDI, M-A-L-D-I, is another technique for ionization and getting molecules into the gas phase. It's matrix-assisted laser desorption ionization. Talk more about all of these techniques in a second. All right, so the gist behind chemical ionization is that a reagent gas is going to be used to protonate the molecule. You're going to put a proton onto the molecule. Sometimes it'll be another ion, but you'll do so with a reagent gas. What you're doing is first ionizing the reagent gas. But unlike the conditions where we're doing ionization in mass spec, which are very, very powerful vacuum, very high vacuum, we're doing that under a weak vacuum at about 0.5 millimeters of mercury. Now, what's happening under those pressures is that your ions that you're generating of the reagent gas of methane or ammonia or isobutane are colliding with each other. And what they're doing is making acids. So for example, as I said, methane, isobutane, or ammonia. So let's look at the chemistry of the reagent gas. So we saw that if you take methane, and you give it a good hard whack with an electron, you get a methane radical cation. You get CH4 plus dot. In the gas phase, when CH4 plus dot collides with another methane molecule, what happens is you transfer a hydrogen, and so you get CH5 plus protonated methane. In other words, you basically glommed a proton onto the methane structure. As you might imagine, this is not all the 5 hydrogens sort of stuck happily around one carbon. One is sort of glommed onto the side of the molecule. As you might imagine, this is a very strong acid. And if we're going to balance our equation, we also get a methyl radical. So now when you have this very strong acid, CH5+, and it collides with your molecule, which has come off of the heater coil, now it transfers a proton to the molecule to give you MH plus CH4. And that's very easy to conceptualize. If the molecule has a lone pair of electrons, you protonate the lone pair of electrons. If you have an ether, you protonate the ether. If you have an alcohol, you protonate the OH group to give you a protonated alcohol. If all you have in the molecule is an alkene, you protonate the alkene to give you a carbocation. So we call this species a quasi-molecular ion. And of course, the big distinction is this is at M plus 1. In other words, it's 1 higher than the molecular weight. And sometimes you'll see other things glomming onto the molecule, including alkene fragments in CI mass spec. So methane gives rise to the CH5 plus as your reagent acid. Isobutane gives rise to a tert-butyl carbocation. And at first you might say, well, wait a second, that doesn't look like an acid. But of course, if you think about a tert-butyl carbocation, it can give up a proton off of the adjacent carbon and give you isobutylene. So the tert-butyl carbocation is also an acid in the gas phase. It's less of a strong acid than CH5+. This is really unhappy. This is only somewhat unhappy. So the ionization conditions generate a lower heat of reaction. That's important because that means when that proton, remember this is in the gas phase, so when a reaction occurs and the reaction is exothermic, the molecule is hot. It's vibrating very strongly, and it is still prone to fragmentation. So the less energetic the ionization, the less enthalpic the ionization process, the less energy, the less strong the acid, the less prone the molecule is to fragmentation, and the more likely you are to actually see a quasi-molecular ion and not some fragments. Ammonia, although we don't usually think of the ammonium ion as being strongly acidic, in the gas phase, the ammonium ion is a strong acid because it gets its stability in water from being solvated. And here, you have no solvation. You don't have hydrogen bonding in the gas phase. So even the ammonium ion is a strong acid in the gas phase.
This is kind of like a useless question, but do you get polymerization in a mass spec of radicals?
Do you get polymerization of radicals in a mass spec? Because mass spectrometry is conducted under conditions where your molecules are not typically colliding, you will not see polymer. In ESI mass spec, which we'll talk about in a moment, because the molecules are actually starting in solution phase, you may ionize a pair of molecules that are already stuck together. So you may, for example, see a molecular ion that's derived from 2 molecules and, let's say, 3 charges. So, but yeah, you do not typically see polymerization.
So here with methane for the CH5+, that is the M+1?
So you're not going to see the CH5+, but when you get your molecule, so let's say your molecule is diethyl ether. So now what you'll see is not something, diethyl ether is 29 plus 29 plus 16. But what you will see then is not something at, what's 29 plus 16, not something at 64, if I'm doing the math correctly in my head. No, wait, not something at 74, but rather something at 75 for the protonated ether.
Right. So for that's for methane. So you see that when you have methane, you see that M+1.
You see the M+1.
For isobutane, it looks like it would be one less.
So isobutane acts as an acid as well, and I'll draw a curved arrow mechanism. So I'll just draw this as base. The base takes off the proton. And this is exactly the microscopic reverse of the reaction that you get when you protonate an alkene. So you end up with isobutylene and BH+. And if you think about it, if you protonate isobutylene with a strong acid like sulfuric acid, for example, in a Friedel-Crafts reaction, the first thing you do is you put a proton here, you get a tert-butyl carbocation. So this is just the microscopic reverse of that process. Good question.
How do you have the electron specifically target the methane and not your molecule?
Because you have an ionization chamber first. So you basically have a chamber where, remember I showed you the electron beam? So you have a chamber with methane that's at a higher pressure, that's at about 0.5 millimeters, and an electron beam going into that. The methane is getting ionized, it's colliding, and then it's diffusing into a region where you have the heater coil in your sample. Now the problem with CI mass spec is you still have to get your molecule into the gas phase. And so for a very, very big molecule, this may not be feasible by heating it even in a strong vacuum because the molecule may not vaporize, it may just decompose, right? If you go ahead and you heat up sugar a lot, you don't have the sugar boil, you have the sugar carbonize. And similarly for other organic molecules, they may simply carbonize and then you get those roasty, toasty caramel smells, but not the smell of actual sugar. Soft ionization techniques in which the ionization process gets the molecule into the gas phase solve this. Fast atom bombardment was, I think, the first one developed. And in that case, what happens is you take an atom that's moving quickly, and you actually do that by an electrical process to ionize, accelerate, and reprotonate that, to reneutralize that atom. You have your sample on a target, and you have your sample in a matrix. Matrix is just another way of saying a viscous solvent. The matrix is like glycerol or nitrobenzyl alcohol. And what happens is when the atom fires into the molecule in the matrix, you sputter off molecules, that some of which are protonated, so you basically have the molecule essentially get protonated, and you'll see MH plus or MH plus dot matrix. In other words, sometimes you'll see a molecule of glycerin or a molecule of nitrobenzyl alcohol complexed with your molecule. So this is good for highly polar compounds and non-volatile compounds and higher molecular weight compounds. It's also good for compounds that tend to fragment in CI if you want to see the molecular ion. As I said, there's a variant of Fab called LSI mass spec. In liquid secondary ionization mass spec, rather than firing an atom, you're firing an ion, such as cesium plus, but it's the same basic principle. You put a good hard whack in there, and you end up ionizing the molecule and getting it into the gas phase. I don't want to give hard numbers, but let's say up to about 20,000 molecular weight. So this really opened up a whole new realm of mass spectrometry, including biomolecular mass spec.
Is that for the fast atom bombardment?
For fast atom, well, both of the techniques, but fast atom was the one that first was popularized. John Greaves does the LSI technique. And again, I'm sure he will wax poetic on the differences between the two techniques, but for your purposes, they're pretty similar.
All right, so does that change the type of detector you can use if the molecule's really big?
It does. You end up having to have, well, you can go with stronger magnetic fields, or I think typically this is done with a quadrupole. And then for MALDI, which I'll tell you about in a second, often people do time of flight because time of flight tolerates even bigger mass range. ESI is another technique that's widely used now. These are our open access instruments. Mass spec has become very populist, very cheap, very easy to do. And one of the reasons for this is because a regular EI mass spectrometer is a relatively fussy instrument, although they're often made into parts of gas chromatographs and so forth, but they often require a lot of care. ESI now is a lot easier to care for. It goes up to very high molecular weight. I don't know, I'll say maybe 5 million, but basically just very, very large. So the basic gist is you're spraying off of an electrically charged nozzle, you're spraying charged microdroplets sprayed into a vacuum. And what happens is the droplets in the vacuum, they're in solvent like methanol. The solvent evaporates. The charges, which are put on electrically, get closer and closer together as the solvent evaporates until they repel each other and the droplets shatter apart. And then you have more evaporation and more shattering. And eventually you get charged species free of solvent. So you often end up with multiply charged species for big molecules. I'll say big biomolecules. So for example, you will end up with MHN plus. So for example, you might end up with 3 protons on your molecule. Often you will pick up sodium. So you will end up, for example, with a certain number of protons and a certain number of sodiums on your molecule. The sodium cation will give charge to it as well. So anyway, I'm going to show you an example of this in just a second. I'll show you an example of an ESI mass spec. Let me just mention MALDI, another technique that John has in his facility. So you're using a laser, blast the molecule in a matrix. The matrix is a species with a chromophore that absorbs the laser light. And again, you get protonated molecules. So again, you get, for example, MH plus. And again, this is good for very high molecular weight. I don't know, I'll say up to approximately 300,000 molecular weight, but again, very, very large. Mass spec has gotten coupled widely with other techniques, including separation techniques. So you will see mass spec on a detector of a gas chromatograph. You'll see mass spec on the back end of a detector of a liquid chromatograph, for example, HPLC. And you'll even see hyphenated techniques where you have mass spec coupled to mass spec, where you fragment your ions in a controlled fashion to learn about their structures. So as I said, in these soft ionization techniques, what you're doing is taking the molecule and putting a proton on it, or a sodium ion. So for example, to give you MH+, for example. So I'll just give you two trivial examples. You wouldn't typically look at methanol, but it's a nice simple way to think about it. If you put a proton on methanol, as I indicated before when I talked about diethyl ether, you will end up with protonated methanol. You have sodium from glass everywhere. And so if you put a sodium on in your soft ionization, for example, in ESI mass spec, you'll end up with a sodium on your molecule. And what I want to do now, sometimes you'll even see, so this would be M+1. This would be M+23. Sometimes you'll see potassium as M+39. And so what I want to do is show you an actual ESI mass spectrum of a molecule. I have a number of handouts here, or a handout here. And I think we may need to shoo a few handouts over extras. Try not to chop down too many trees here, but I always like to give a few extras. All right, so this, and we're going to be talking more about actual mass spectra in subsequent times. Everyone have a handout? All right, so this is a handout of a particular molecule. This one happens to be an example of a peptide. Now we're going to talk more or less next time, but one of the big concepts is you're separating molecule by molecule, which means you're looking at individual isotopomers. Put simply, 99% of your carbons are carbon-12. 1% of your carbons are carbon-13. So when you calculate a mass for mass spec, you're going to actually calculate the exact mass. That's based on the predominant isotopomers. The exact mass of this molecule is 744.5. And so if you look at the mass spectrum, the first peak you see here is this peak at 767.6. Here you see a peak at 745.7. So this peak is your M plus H plus. The instrument is only good to plus or minus a few tenths unless you're running in a high resolution mode. So in other words, we would expect if we pick up a proton here, we get to 745.5 We're at 745.7. That's within the limits of experimental error. This peak over here corresponds to M plus NA plus. Sometimes you will hear the biggest peak in the spectrum referred to as the base peak in the spectrum. This peak here corresponds to a C13 isotopomer. We'll talk more about that later. That's a molecule with one C13 in here. You'll see the same over here. And you'll notice you even see molecules with two C13s. We typically don't get a lot of fragmentation in the mass spec, but you'll see, for example, here you have a fragment. You're doing acid chemistry on the molecule. What's happening in generating the fragment is you're protonating on this nitrogen, and then it's leaving for that particular fragment to generate an acylium ion. And here's where the concept of charge comes in. The fragment is uncharged, so this is basically, I'll just write etc. for the rest of the molecule. We're fragmenting right at this valine to cleave this bond. The fragment, the charged peak, the charged species, gives rise to this peak here, and this is another fragment over here. All right, the last concept I want to bring to mind is, question? The last concept I want to bring to mind is something very simple. It's what's often called the nitrogen rule, and I'll just play with this for 1 second. Nitrogen rule is that compounds with an odd number of nitrogens give odd M plus in EI mass spec. And you can convince yourself of this. In other words, if you look at trimethylamine that contains one nitrogen, its molecular weight is 59. If you look at isobutane, which contains no nitrogens, it has a molecular weight of 58. And you'd say, okay, that's in the EI mass spec, and everything turns on its head in the soft ionization. Reversed. So for example, M plus H plus for trimethylamine now would be 60. And if you were somehow protonating this, which you might do in the CI mass spec, it would be 59. And so again, on inspection of the mass spec, if you look at the mass spec, you can go ahead and say, okay, this compound has an odd number of nitrogens, or this compound has an even number of nitrogens. The only caveat is with fragmentation in EI, everything can get messed up. So for example, if you take tert-butanol, tert-butanol has a molecular weight of 74, but you're often not going to see the tert-butanol. You'll often see a carbocation in the EI mass spec. You'll often see a tert-butyl carbocation. And that has that's M minus 17, that's 57. And so if you just looked at the peak, the biggest peak in an EI mass spectrum of tert-butanol, you'd say, oh, the highest molecular weight peak is 57. This has to have a nitrogen. In reality, no, it's a fragment. Anyway, that's something to keep in mind as a way with small molecules of saying, okay, what elements are present. We'll pick up next time talking about other elements present. We're going to talk about chlorines, bromines. We're going to review the concept of exact mass a little bit more.